Good evening, everybody. I'm afraid I only have one word of Portuguese, which is obrigado. So obrigado for coming. Oh, and Porto is the other thing, the football team. So obviously that joke. So given that you're all DevOps aficionados, we thought that this would be a good talk for you, which is this is kind of moving the game on a little bit. You know the basics, you know what a deployment pipeline is, you know about the ideas of establishing good feedback and all those kind of things. So what happens when you start growing beyond that a little bit and living with this a bit longer? So these are slightly more advanced ideas, and there's quite a lot of them. It's quite dense presentations, so I'm going to whiz through quite quickly. I'm happy to take questions as we go, but I might have to cut that short if we're running out of time. So we'll see how it goes. If you do have a question that you want to interrupt, put your hand up and we'll try and answer it as we go. So that's the nature of this talk, really. So first of all, does my clicker work? No. Yes, it does. So what is it that we're really looking for? Which we're trying. This is just revision. I'm going to just do a few slides of revision to remind us why we're all in this game in the first place. And what I think that any organisation that creates software is looking for is they want to have an idea, they want to get that idea into the hands of users and figure out what the users make of the ideas. I think that's pretty much the fundamentals of what software development is, and where continuous delivery steps in is that we try and optimise for that. We start off from the principle of trying to make that as fast and efficient and as effective as possible. That's pretty much it. We can walk out home now. That's it. So we do this by establishing these feedback loops, and kind of the three feedback loops that I tend to use as a model. It's only a model. It's much more complicated than this in real world. But at the outside, we've got the idea into the hands of users. At the inside, we've got the kind of the very fast cycle feedback loop of test-driven development. In between, we've got kind of executable specifications and other forms of automated testing to evaluate the system. And we're trying to get beyond guesswork. This is, I believe that what we're talking about when we're talking about continuous delivery is a kind of engineering discipline. This is starting to think really about how you can apply scientific, rational thinking to software development. We're trying to get a little bit beyond guesswork and get more into carrying out experiments and learning from our discoveries and moving on in that way. That's really what we're looking to try and achieve. We're focused on cycle time. One of the tricks that we use to try and drive good behaviours is to optimise, to shorten that feedback cycle from idea to valuable software in the hands of users. And we can use techniques like value stream mapping to measure the cycle times. And this is when I for other talks, I kind of compare a traditional sort of cycle time with a continuous delivery sort of cycle time. And this is a project that was 15 to 20 times more complicated than this one. You could be at the point of releasing production software in 57 minutes in this one, and this one took 103 days. So we work to optimize cycle time because that drives good behavior. I think that if you only did that, if you only worked in a scientific, rational, empirical discovery kind of experimental approach to solving problems, all problems, and you use that technique to optimize for cycle time, you drive out all of agile thinking, all of DevOps, all of continuous delivery, all of lean. All of those things fall out as a natural consequence of just doing those, to my mind. You can't have a fast cycle time for an enterprise system like this if you haven't got a good organisational structure, if your teams aren't small. You can't have a fast cycle time like this if your organisation is siloed. You can't have so you need the collaboration between different groups and different roles. You can't have a good cycle time like this if your system isn't modular and composable in different ways. You can't have a cycle time like this if you haven't got a great story on automated testing, automated deployment, automated configuration mode. All of those things you have to get right in order to be able to achieve it. And we're going to be covering some of those ideas in more detail as we go through. So the principles of continuous delivery, again, we're still in revision mode. So we're trying to create this repeatable, reliable process for releasing software. So we want to automate nearly everything. And if we want to automate everything, we want to keep everything in version control, not just our source code, but system configuration, the dependencies of our system, the version of the operating system that it runs on, the version of the database, all of those things. We want to be able to be as definitive, as reproducible as we can possibly achieve. We want to do things quickly. We want to iterate fast so that we can get good feedback, so that we think we've got more opportunity to learn and adapt and refine our thinking and our understanding and get better and better at the things that we need to get good at. We focus really strictly on quality. We take quality really seriously, and we don't cut corners on quality in order to shave some time off in our delivery, because we know that's going to come back and bite us later. So we focus on doing quality work early in the process, building quality into the system, so that when we get our feedback is honest, it's true, it's correct, it's telling us an accurate picture. We treat done as meaning in the hands of users. We don't, Scrum will often talk about definitions of done for teams. The best definition of done of all is software in the hands of users delivering value. So we need to think about the whole thing. Ideally, we want to be getting information back from production to understand the impact of our software on our users. So things like telemetry and operational feedback are important as well. And we want to work in open, transparent ways so that the process is easy to understand. It's clear where we are as we're working on things and with ideas. And finally, it's a process of continuous improvement. This is not a process where we say, okay, we've had our 6-month continuous delivery adoption process, we're done with that now, we can move on to the next thing. Now for SAP, I don't know, whatever it is. That's not how it works. I think that what we're talking about here is a paradigm shift in our approach to software development. This is a way of thinking. There are problems with the way that most software development works. Let's think again. Let's think again, and we start from the beginning and come up with something that works better. And that's what this is. And from then on and forever after, we're never quite satisfied. That's kind of part of the game. It's a bit like science. I'm a popular science nerd, and you could look at any scientific theory, but let's just pick a big one. So, general relativity. Einstein's theory of general relativity is just over 100 years old. It was invented. The first paper was published in 1917, and that stood up to every experimental test so far. The gravitational wave telescopes that they've started to use to see big bangs, black holes crashing into each other and that sort of thing. Einstein predicted 100 years ago from that theory, and yet we know it's wrong. We know that it's only a theory. We don't call it Einstein's law. We call it Einstein's theory. We know it's wrong because it doesn't match up with quantum physics. If you look at the physics of the very small and the physics of the very large, they don't match up. There's a discontinuity. So we know that at some level, our theories for both of them are a bit wrong. So there are teams all around the world trying to figure out what's a better theory, what better fits the facts. I want to plant this thought in your heads, is that if you think about all of the stuff, around, all of the information around the software systems that you are responsible for, think about the software itself, the multiple versions in the version control system, the documentation of the software, the ideas in people's heads, the way that the team works together, all of that stuff, the soft and the hard stuff around that stuff, is all really the best theory. The requirements for the system is all really just the best theory for how to solve that problem at the moment. It's never the answer. It's never concretely done, because you could always find a way of making it a little bit better. And so if you take continuous improvement seriously, that's kind of part of the game. One of my friends, Dan North, has started talking about one of the things that he suspects is a good measure for high-performing teams is what he calls the software half-life of the team. So how long does it take your team to rewrite half of the software that you're responsible for? And his subjective impression, and which matches mine, is that the best teams are probably talking about rewriting half of the software that they're responsible for, probably in the order of 3 to 6 months. Every 3 to 6 months, they've rewritten half of the software, always. There are other organisations that never rewrite half of their software. They're just stuck with what they had 40 years ago, and they're still trying to make that work. And that's a very, very different kind of mindset. It's a very different way of thinking. And one of the reasons why all of the automation and all of the processes that we talk about are so important is because it allows that opportunity to keep refining and improving and thinking of better ways of doing things. The other kind of bit of revision, the crucial idea in continuous delivery is really the idea of the deployment pipeline. And as I get older and grumpier, I kind of get harder line in some of my views. And these days, I kind of think, well, you know, if I'm writing the simplest software system, I'm probably starting off with a deployment pipeline these days. Unless it's completely throwaway, I'm going to build a deployment pipeline for anything that certainly anything I'm doing in a professional capacity. But even if I was doing something like writing software for my mum's cake shop, I would write the deployment pipeline. And my simplest deployment pipeline looks like this. That's it. So we've got some developers that are committing to a version control system. We're going to have some commit tests that are going to give us a fast feedback, some unit tests, very fast, going to run very quickly. We're going to have some higher level kind of functional tests that operate the whole system, deployed to lifelike circumstances. We're going to have an artifact repository that we're going to, you know, the build results that we're going to deploy to production. That's all the basic deployment pipeline. For most commercial systems, you probably want a bit more to it than that. So the picture that I tend to use for a more fully fleshed deployment pipeline looks like this. And this is relevant because we're going to be exploring, we're going to be using this as kind of a model for some of these ideas as we go through this evening and kind of think about these things. But this is where we're going to be focusing much of the discussion tonight. So this is kind of a more fully fleshed deployment pipeline. This is modelled on the 57-minute system that I was talking about before. I was hired to work as the head of software development for an organisation that was building one of the world's highest performance financial exchanges. It's a company called LMAX. And we built this seriously difficult high performance computing system. And I was in the middle of writing my part of the continuous delivery book at the time. So all of those ideas were fresh in my head. We had a blank sheet of paper, so it's kind of like a clean room of experimenting with what you could do with continuous delivery. The entire enterprise system would go through the pipeline and give us results back in 57 minutes. So we did the fast cycle tests, the functional test from the perspective of users, manual testing where it was, that's not quite in the 57-minute cycle, but we'll figure that out. Performance testing, security testing, resilience testing, all of those things, data migration testing, and if all of those tests had passed, there was no more work to do, and that took 57 minutes. There was no more work to do before we were happy to release it into production. We could push the button and go into production. So that's what we're talking about in terms of the deployment pipeline, which is going to be the theme for much of the rest of what we talk about this evening. So a good place to start then, if the deployment pipeline is that important, is what's the scope of a deployment pipeline? So one of my other nerdisms is that I'm interested in aeroplanes and flying, so I picked that as well from my picture. So here's a picture of an aeroplane, and you know, what's the scope of the deployment pipeline? Because you know, are we going to deploy the whole thing, or are we going to deploy bits and pieces of those things? You know, what's the sensible scope for us to test together? If we deploy just the whoops, sorry, go back. Sorry. If we just deploy, let's say, that bit, we don't have a working system. It doesn't work. None of these bits on their own work. This should be ringing bells for you. You should be thinking, oh, is he talking about microservices? Because I'm talking about microservices. So this is about how you decompose your system and how you're worrying about the dependencies between them. If these things don't fit together well, you haven't got a whole system, and you don't know whether that's a problem until the point at which you release them together. So I think that the first point is you want the scope of your deployment pipeline to cover what you consider to be an independently deployable unit. Whatever that is. If that's a microservice, you should be happy to make changes to the microservice, run all of the tests in your deployment pipeline, and do nothing else before you push it into production. You shouldn't feel the need to have to test that microservice with other microservices. Because if you're doing that, then that should be the scope of your deployment pipeline. So it's the deployable unit that defines the scope of the deployment pipeline. The reason for this is going back to the theory that I was talking about earlier. We're trying to get away from guesswork. We're trying to get away from guessing. We want to know that our software works and is ready. We want to test. If I'm doing something serious, like an exchange or a healthcare system or something like that, I want to know that the configuration that I deploy into production is going to work, whatever that is. So the starting point, the scope of the deployment pipeline is an independently deployable unit. Now, it might be that you've got one independently deployable unit, or you might have a cluster of different independently deployable units. We've got a formation of aeroplanes here. Each of these, we could still have a deployment pipeline for each one of these separate things and deploy each of those independently, because they don't actually have to be deployed all together. If this one was different from this one, it wouldn't matter very much. There's limited interaction between them. So that gives us the option to be more flexible, and that's kind of the root of microservices. But the crucial step in achieving a microservice style scale up is to be able to make sure that those things are loosely coupled and separated at the level of being able to comfortably feel happy to deploy them without needing the worry to test them all together. As soon as you start to test them all together, you're slowing the whole process down, and you're back kind of in the world of nasty waterfall style processes where you're not really going to know whether your stuff works until much later. And remember, we're optimizing for fast feedback. One thing that I should have said that I didn't say is what's the scale of the feedback. On the whole, I recommend that people aim for under 5 minutes from the commit stage and under an hour for the whole cycle. That's challenging, that's hard, but it's achievable on surprisingly massive scales if you take it seriously, and if you're prepared to invest in the engineering and time to manage that to speed those things up.
Including manual testing in that 1 hour.
The manual testing is a little bit of a red herring. So the way that I usually describe this is that I think that we should automate any kind of test that we want to do more than once. So anything that we want to repeat more than once, we're going to automate. And so that kind of cuts that. There is no manual regression testing. So manual testing is purely exploratory. It's about, does it feel nice to use? And so those kinds of bugs that you find from that sort of testing are a little bit softer, a little bit less serious. The software is going to work because you've tested that with your automated testing suite. It's just whether it's nice to use, and those sorts of things, the buttons the right colour, does the text line work, those sorts of things are the sorts of things that manual testing is largely going to find. It's going to find more important things than that as well, maybe. But those are the sorts of things that it's looking at. So it could be slightly out of band. So that's not strictly in this 57-minute cycle because people don't work that quickly. So on the whole, the way that I usually set it up is that the 57-minute cycle, or the sub-hour cycle, is the automated, that's the repeatable, reliable, automated testing approach. And I trust that the team are collaborating sufficiently that if something serious crops up, they're going to catch it early enough that it's not going to kill it. And plus, human beings are not going to find the sorts of things that are going to kill us because we've tested all those using automated testing on the whole. Right, so we want these things to be independently deployable units. That's the scope of deployment pipeline. I gave a version of this talk at a conference in London last month, and as ever, this is the most contentious thing that I ever talk about: branching in software. So I'm expecting to have a debate. I'm expecting you not to agree with me, a significant proportion of you not to agree with me. There's a limit to how much detail we can go into. So after the talk that I did, I wrote a blog post. So if you don't, and there's been lots and lots of chat after the blog post. So if you want to read up more detail about this, I'm going to refer you to the blog post. But let's talk. Let's start talking a minute, and then you can start throwing things. So where to branch? We're trying to optimize from having an idea to getting that idea into production. So we want our process and our mechanisms to allow us to do that as efficiently as possible, so that we can get feedback as quickly as possible. So let's imagine that we've got a bunch of developers, each working on different features, and they're working on feature branches to isolate those features from the rest of the system. So where is it sensible for us to test? Well, we could test there, and that's no use at all because there are going to be changes that come afterwards. We're never testing some combinations that end up in production. We could test there. We could test after actually each of the merges into production. That's safe. That's good, and it works as long as these branches don't live for a long time. As soon as these branches live for a long time, what that's doing is it's meaning that the people working on those branches don't know whether their software works until the end. And that's too late. It's too late to find out that you're screwing up after you've screwed up. You want to find out that you're screwing up while you're in the middle of screwing up so you can stop screwing up. So we don't really want to push it out there. So there's the compromise. You could make sure that these branches don't live for too long. I added something to the definition of continuous integration. The bit that I added was that you're not really doing continuous integration if you're not merging your changes onto master at least once per day. That's quite a hard-line statement for some teams, because what most teams, my perception is that what most teams do these days, because great distributed version control systems like Git promote this kind of idea, is that they'll start working on a feature and they will commit changes to master when the feature is finished. That's kind of what my understanding of the definition of feature branching. But as we've just learned, if we wait until we get feedback only at the point at which it's finished, that's way too late. It means that we're going to regularly be breaking stuff if we do that. So if we could make our feature branches only last for less than a day. That's one strategy. And we could test on the feature branches as well. But if we do some work over here and we do some work over here and we're merging those together, we're never testing the combination of those two features together. So we've got to also test at the point of merge. So now we've got to run the test twice, at least twice. We've got to run them at least once on each branch and at the point of merge. So that's inefficient. We just slowed down our ability to make changes really fast on the route to production. We're going to defer our feedback again. So that's kind of a bit annoying too. That's going to get in our way of going quickly. So I think that the safest way, the combination of the safest way and the most efficient way is to try and do without the branches. Work always on trunk. So you make a change and you commit it to trunk and it does the continuous integration things, it runs all the tests and say, oh yeah, I've just broken everything. I'll back that change out. I'll try and figure out what went wrong, and then you do something else, you commit it and say, oh, that's okay. But that does change the way that you work. The common pushback is, yeah, but how do you build big change? What about big complicated things? Well, you do it in lots of little steps. And continuous integration imposes some compromises on us. If we're going to work with continuous integration, it means that we're going to be prepared to commit changes, allow them to go into production that are not yet used. It means that we're going to use things like dark launching, feature toggles, branch by abstraction, those sorts of techniques to allow us to work in that way. But my subjective impression of doing this for a long time, and doing it wrong lots. I've done all the branching stuff. It's not that I've not tried that, but I've never been able to really make that work as well as working on head, given the compromises, working on head and doing the regular commit all of the time. That's kind of backed up. So last year's State of DevOps survey by Nicole Fosgren, Jez Humble and Gene Kim and the Puppet Labs folks said that teams that work on trunk like this tend to be higher performing than teams that work on feature branches. That's a very contentious thing to say in our industry at the moment, because teams like their feature branches. It's a lovely thing as a developer. I like it. As a developer, wouldn't it be lovely if I can kind of write my code and ignore what you're doing? I'm just going to put it to Mike. You don't exist. I'm just going to work on Mike. That's lovely. That's really nice. Except it's not true. Except it's hiding information. My kind of tagline here is that branches were invented to isolate change. They're invented to hide change from one part of the code base, from other parts of the code base. That's what they are for. Continuous integration, the clues in the title, is about continuously integrating changes, and so they're kind of opposites. They're kind of opposite things. You can compromise feature branching and compromise continuous integration and get something, but I don't think it's as efficient as just drink the Kool-Aid, work on trunk, and go faster. If you take my advice and you do the feature branching thing, but your feature branches always live less than a day, I'll say, okay, I can't complain. What you're doing is continuous integration, but I think you're a bit mad because now you're doing more work than you need to because you're doing it on branches and there's no need. If you're committing once a day, you might as well just commit to master once a day. Who cares? So that's my branching thing. If you want to read more about that, I've got a blog site called davefarley.net. And there's a blog post on there that goes into that more, and you'll see lots of people arguing with me and pointing me out while I'm talking rubbish. Right, so my advice for branching is don't branch. Don't branch. Don't branch. So, moving on. So as we move on, what we're getting to is the pipeline is the only route to change in our production system. All change goes through the pipeline. Therefore, it's kind of important. Therefore, if your pipeline breaks, you're stuffed. You can't make any changes. If your pipeline is broken for any significant amount of time, you're blind, as well as not physically able to make things into production. You don't know whether your changes work together with everybody else's. So it's really important to think about that and start taking it seriously. So, we're going to go through now and talk about some various pipeline problems. I want to just one more recap because we've kind of gone through a few different, wandering around different angles on this. So one more recap. Remember, the kind of prime directive is we want fast, high quality feedback. That's what we're always looking to achieve. We want to make small changes frequently and get great feedback on those. Really fast. That's what we're trying to do. And so the performance of these things is really important. So common pipeline problems. We could have a slow commit stage. We could have a slow acceptance test stage. We could have failing tests. We could have intermittent tests. And we could have pipeline changes. We could try and make changes to the pipeline itself, which break things and make us blind. So I want to explore those in a bit more detail and think about those. So let's start off with slow commit stage. The commit stage is probably the highest value bit of real estate in your system, maybe except for the developer's ID. If I could get my performance test results in the form of a red squiggly line as I was typing in my ID, I would take that. I would love that. But I don't know how to do that. And so the next best thing is to move them out to things that happen in the commit stage, and that I want fast feedback. I want feedback in under 5 minutes. After that, I'm going to go further out the pipeline. I'm going to delay things further, and I'm kind of, the worst case for me is that I don't want to go more than about an hour without knowing that I'm in a releasable state. So that's what I'm trying to achieve. So we've got to change the commit stage, and we're trying to get this fast feedback. A commit stage is typically, for most technologies, made up of this kind of little pseudocode algorithm. You're going to compile some code. You're going to run some unit tests of some kind. You're probably going to do some sort of static analysis of some kind. And you're going to build these installers, the jars, the .NET assemblies, the Docker images, whatever your deployable unit is. You're going to create those as the outcome of a successful commit stage. And from then on, the rest of the pipeline will test those. So that's kind of what we're doing. So each of those, there might be problems. The ideal cycle time from the commit stage is 5 minutes. So we want to be able to do all of these things in 5 minutes. First problem. Okay? And yeah, I'm talking ideals, but there's a good reason for the 5 minute thing. I don't have data, I don't have strong data for this, but my subjective impression is that the longer that you wait for results, the more you'll have failing tests. If you do an overnight build is probably in the top 10% in terms of quality of software development in the industry. That's pretty good, an overnight build. If you do an overnight build, my guess is that you're regularly living with somewhere between 5 and 10% of your tests always failing. We don't want to do that. We want to work on it. We want to trust our tests and keep them working. So we want to reduce the cycle time. 5 minutes is fast enough that it feels almost free. It feels, even if I'm committing every 15 minutes, 5 minutes is just barely acceptable. If it's 10 minutes, I'm going to start delaying. I'm going to commit less frequently. I'm going to back off. I'm not going to go as fast. And so the size of the batches is going to increase, and the possibility of merge conflicts is going to increase. All this stuff gets more complicated. So this is the most valuable real estate in the pipeline. So architecture system, so you can get kind of compile time feedback in your IDE, that's good. But after that, this is the most valuable real estate. So we want our builds and our test executions to be really efficient. This is a really valuable place to invest lots of time and money and resources on making this fast. So if you can throw hardware at it, that's fine. Buy big servers. Run the build from RAM disk if that speeds things up. I've done all of these things. You parallelize it, have incremental builds. All of these things are good techniques. So this is a good place. You don't want to cut corners at this point. So the first thing that can go wrong is compilation. So the first thing to think about is make sure that your builds are efficient. So think about, go and rewrite the builds. Think about making them, nicely coded. Make sure that they're modular. Make sure that they're loosely coupled. Make sure all of those things that we know to do in software. Apply that same kind of thinking to your build scripts. Buy faster hardware. Buy big boxes. Hardware's cheap. You can get a really, really fast server for $10,000. Developers are expensive. so spend money on some hardware. That'd be good. That'd be okay. Parallelize the build. Modern build systems are really good. Incremental builds. I worked with some incremental build systems back in the day that were a bit flaky. The modern ones are rock solid. Google treat all of their software except for Chrome and Android as one thing. It's in one big repository. And my understanding is that any developer commits a change, it evaluates the whole thing, builds the whole thing, the bits that it needs to, but ensure that effectively the whole thing is built and tested, and they get feedback in a handful of minutes. You can do this on a massive scale. That's 31,000 developers that Google have doing that, working in that one repository. So parallelize the build, use modern build systems to help you do that. Decompose your system into independent modules. This is a tricky one. This is the one that everybody kind of from a traditional organization instantly thinks that's the answer, that's what we'll do. But it's tricky because one of the hard things, I think ultimately there are probably two seriously hard things in computer science. One of them is concurrency and parallel computing. And the other one is dependency management. And as soon as you make your services independent, this goes back to the pictures of the aeroplanes, as soon as you make those services independent, you've got a dependency problem. However loosely coupled your services are from one another, if they don't plug together and work together, and you don't know that, you're in trouble when you release into production. So you've either got to design the protocol so they're really, really well abstracted and really arm's length, and effectively you're writing this independent thing that's treating the rest of the world as hostile, or you test them all together. Both strategies work. Both strategies scale to an enormous degree, but this isn't as simple as it sounds. Nearly all of my clients, the bigger ones, the more traditional ones, think that's what we'll do. So how do we modularize our system? Well, that's really quite hard. If you've got a legacy system and you start teaching that, and it's tightly coupled, it's really quite hard to start pulling those things apart and making those independently deployable. That's a hard thing to do. So there's definitely mileage here. This is part of the success behind Amazon and Netflix and those sorts of organisations. There's definitely a model, but you've got to be quite sophisticated to be able to make this work. This isn't an easy model. This is a harder model. I think in many ways the monolithic model is actually, the problems are simpler. They're more tractable. buy lots of hardware, do lots of smart thinking, paralyse the hell out of it, is probably a bit simpler than this at some level. But this is the one that you get the real massive scale from. It's not easy as it first seems. Dependency management is one of the really hard things. Microservices, there's no silver bullet in microservices. I see too many teams that say, oh, we're a microservices team. But I don't really trust that my sort of stuff works with them, so I'm going to test those together. And then I don't really trust that that works. I'm going to test those together. And they end up just testing the whole stuff together, and they don't know that their stuff works for 3 days. So. Compilation. So look at a modern build system. There are off-the-shelf open source build systems that are remarkably good. Gradle is good incremental build. Bazel is the Google one. Buck is the Facebook one. The company that I used to work at, when I left, our commit stage took 4 minutes. They switched to Buck, and they got it down to 40 seconds. It's worth doing the experiment. It's worth taking the time out to think about those and investigate them and evaluate them, see if they're a good fit. There's some clever things out there. The Facebook thing in particular, they've got, I think Google do the same thing, but effectively you've got distributed cache. And so if the stuff is built once, ever, anywhere in the organisation, it's then reused everywhere. So it's very efficient. Try running the build from RAM disks, certainly for things that are I/O bound, like traditional compiled languages, like C++ in particular is the one that I've done quite a lot of this with. It makes quite a significant difference because C++ tends to be lots of small files, and the build tends to get I/O bound. So if you put it in solid state disk, that improves it. If you put it in RAM disk, that improves it a bit more because the bandwidth is higher. Tests, slow testing. So look to the tests. Think about the tests themselves. The problem here is not the donkey. So if your tests are slow, go and address the tests. Start rewriting the tests. Start doing things to make them better. The commit tests, mostly you want them to be pure unit tests. You don't want them to start the application, talk to disk, talk to the network, even start another process. You want them to be running really, really close to the code under test, and that way you can run tens of thousands or hundreds of thousands of them in the 5-minute window that we're talking about quite easily. So we don't want to do these sorts of things. We want the test and the commit stage to be really fast and efficient. This is the territory of test-driven development. Test-driven development is your friend here because it allows you to build the right kind of tests that are loosely coupled from the system under test, and you can keep changing the system without breaking it. Select slow tests grudgingly. Occasionally, you might have a test that is really important. It tells you something important. It catches the kinds of bugs that you and your team are always putting into the code. But you can't come up with a way of making it faster. So maybe, if that's the case, it's worth having the slow test. But you should always question a slow test. You should always wonder whether it's paying for itself. Tests are funny. There's a joke about advertising. Somebody goes to an advertising executive and says, how much is your advertising budget? And he says, £3 million. And he says, how much of it works? And he says, about half. But I don't know which half. And tests are like that. So however many tests you have, actually tests, you don't know whether they're doing anything for you until they start failing. It's only when a test is failing that it's actually useful. When it's passing, it might be telling you something useful, or it might be lying to you, you don't know. When it's failing, now it's time to go and look. So take them seriously. You want wonderful, I'm the last person on the planet probably to tell you not to do automated testing. I try and test everything in the sorts of systems that everything I can think of in the sorts of systems that I build. But you have to, if there's a slow test, you need to think seriously whether it pays for itself. Always think about efficiency when writing tests. Try and make it, just have that in your DNA. If you're going to iterate over a list in a test, it doesn't matter if there's a million things in it. There's no difference. You use chicken counting, 1, 2, or many. Sorry, 0, 1, or many. So nearly all of my loops are I do them for 3 things, which is 1 more than I need to. Usually doesn't matter. So because that's enough. Because if it's multiple, 3 is enough. 3 counts as many. So you don't want to iterate from lots of things. Use mocks and stubs to mock out dependencies so you can get answers really quickly. Periodically, sort the tests and have a day. Make it a bit of a party. Maybe have prizes for developers to speed up the tests. But sort the tests and rank them the slowest first. And then have a day where you just go and you try and pick the slowest test up and try and find a way of making it faster. Or deciding whether, actually, this one's slow and horrible, I'm just going to throw it away. Sometimes that's a good decision. Run tests in parallel. If you follow the general advice for automated testing, you want them to be atomic. Which means that you can run them in parallel, which is great because now you can start distributing. Actually, the limit is there's a little bit of overhead to get everything up and running, and then it's the duration of the slowest test. You can imagine having 1 computer or 1 node in your cluster for every single test, and that's kind of the limit. You're probably not going to go to that limit very often, but you can start certainly speeding things up. If this is difficult, it means that your test is badly designed. It means that you've got poor isolation in the test, and therefore fix it. That's it. There's no more advice than that. Fix it. Just don't live with the pain. As a last resort, this is more of a tactical thing, which I've done a few times. When you're trying to introduce continuous delivery to teams, and then you're trying to get them up and running and going, and they've already got a bunch of slow tests, which is quite common if they did unit testing rather than test during development, direct the test after the code was written. They're often slow and more complicated. Then arbitrarily, I'm going to say that any test that runs for more than 2 seconds is going to be called an acceptance test. And you're going to be moved into the acceptance test stage, and anything that's under 2 seconds is going to be called a commit test and run into the commit stage. I've had some success with that. It's a bit pragmatic, but it can work. It's not really strictly in the kind of the ideals, but it can move you forward. So static analysis. Static analysis is wonderful in the commit stage. One of the things that I'm particularly keen on is an automated assertion of my coding standards. So if I put some code that breaks my own rules for coding standards, it's rejected by my deployment pipeline. I quite like that. It kind of keeps the quality of the code up. And there's other forms of static analysis that you can do. If you want to do more complex thing like cyclomatic complexity analysis and all of these sorts of things, which give you good information. And again, fail the build if it doesn't work. But that can be quite costly. So you've got to be careful again that doesn't the cost of that doesn't creep up and start slowing down the build. One of the things to bear in mind that I haven't said explicitly, but as you start living with these things, you're going to have an ever-increasing number of tests. Your software is presumably going to grow and get more complicated and more functional, and so need more testing. And so this is an ongoing problem. You're always going to be going through a kind of cycle of, oh, we're flying, we're going really, really fast. Oh, damn, it's taking 10 minutes to get the results. Let's do some work on that and speed it up. Yeah, we're flying, we're going really, oh, damn, it's taking 10 minutes. It's, that's just going to be your life from now on, really. So static analysis can give really useful feedback, but it comes at a cost. It needs to pay for itself. So the first thing is it needs to be valuable. So if you're doing static analysis and it's telling you all sorts of fun things, the cyclomatic complexity, if your code is beautifully factored on the whole, doesn't matter, then running a cyclomatic complexity is probably going to be a waste of time. And doing it on every build might be a bit of waste. So you need to think about the value that you're getting out of it. They need to be worthwhile. And if they're not catching real bugs, drop it. That's one of the harder decisions to make, because we do all this, we invest in all of this stuff to automate all of our things and get this great feedback, and then we say, yeah, we're not going to do that anymore. And that's quite a hard decision to make. Emotionally, it's a difficult thing to do, but you've got to. The feedback is the golden rule. The feedback, so the speed and efficiency of the feedback is the target. So last resort. Again, what's the value of the feedback that you're getting from those things? Is it worth slowing the feedback cycle down? I would argue it's almost never worth that. There are other ways of doing it. You can tackle those sorts of quality issues in other ways. And I think that the value of the feedback is so enormous to quality that I would dump the analysis before I dump the fast feedback. So I would tend to give up on the static analysis as a last resort, if that's what it came to. I like the static analysis, but there are times where I've said, let's not worry about that for now, we won't bother. So we want to test release candidates that may make it into production. We want to test them in lifelike circumstances. So we want to create the installers. We want, if the commit stage is successful, we want to build the thing that we're going to deploy into production. And that's what we're going to test from now on. And normally that's part of the commit stage too. So building the creating the installation might be problematic. I had a client last year. Their build directory in their system was 114 gigabytes. We looked at it in a bit more detail, and 112.5 gigabytes were test data. So in their build, they were shipping around 112 gigabytes of rubbish. And that slowed everything down, just the network costs, it slowed everything down. So we took that out and they stopped doing that and their build sped up. So think about those things, think about the efficiency of what's going on. Start thinking about trying to make, your deployed images as lean as they can be. So the output of a successful commit stage is production deployed software. And sometimes this is hard. For some technologies, this is a difficult thing to get right. But I've yet to see a way where you can't kind of work around it. I did some work with a team that were writing software for FPGAs. So the production system for an FPGA is hardware. It burns the hardware. And we're now into the realm of physics. There's only so much you can do about speeding that up. So we did loads of stuff in simulation first, so that the burning always, as close as we could get it, always worked. It was a non-event, and so that was okay. So there's lots of ways, but you need to think about this carefully. So if creating installers, this is not usually a place where stuff goes wrong. If you've built if the software is all compiled, it's passed all of its tests, you don't really usually get bugs when you're building the installers. If you do, you're doing something quite seriously wrong. So make sure that that's reliable, and at that point it doesn't really matter in terms of the commit stage, whether you're in the commit stage or out. It's going to have a cost for the whole pipeline, of course. You can't avoid that. But remember, the commit stage is this hyper-valuable real estate, and so it's worth trading that off to get the fast feedback if you can't get these builders, the installers created as part of the commit stage. I think mentally, it's the right model to think that the result of the commit stage produces an installer. That's the right way of thinking about it. But practically, the performance kind of cheats a little bit here. I'm going to skip over this because I'm going to go through it very quickly. So, human continuous integration. So this is kind of the interaction between the people and the technology to get good feedback and to make sure that this works as a team. And there are sort of silly things that are important. So we're going to commit our change and we're going to wait for the results of the build. It's one of the reasons why we want feedback in 5 minutes. We're not going to go home. We're not going to go to lunch. We're not going to make the coffee. We're going to sit there and we're going to watch the build, so that we are the first person that notices if we commit something that breaks it. If I break the build, I want to be the first person that knows. And if I'm not the first person that knows, that's a build sin, and I'm going to have to pay for it in some way. I've variously worked in teams where if you committed a build sin, you had to wear a silly hat until the next person committed a build sin. At LMAX, when we were building the Exchange, we had a sin jar. And if you committed a build sin, you had to put £1 in the jar, and then every now and again we go to the pub and we drink the contents of the sin jar. Sorry?
They dropped the number of commits.
Only after we've drunk the So, we want to fix or revert failures in 10 minutes. This is a really good practice to kind of, this is one of these soft things, but try and build the discipline in the team so that if I commit a change that breaks something, I'm now on the clock. I've noticed that I've done it, and now I've got 10 minutes to figure out what went wrong and commit a change that fixes it, or I'm going to revert my change so everybody else can carry on working, and I'm going to spend more time thinking offline about what's gone wrong. If somebody breaks the build, even in a later stage, and you notice before they notice, it's still a build sin. So once you've committed your change and you're working on something new, you're still going to be keeping an eye out for what's going on for the rest of the build, for your change. You're watching your change go through the pipeline. That's kind of what the transparency is. One of the reasons why I much prefer to have big displays with pictorial images of the deployment pipeline than I do having email sent to me, because I can ignore the email, but if I've got a big red thing up there, everybody knows that I've screwed up, including me, and I can just glance and say, oh, I've screwed up. So I get really good feedback that way. I'm going to skip over some of these a little bit. So, in summary, performance of the commit stage is really, really important. This is where you want to invest your principal engineering and spend. Teams with a fast commit stage keep the test passing because it's easier to iterate and fix things more quickly. It's much easier to keep all of the tests stable. So invest in the commit stage. Acceptance test stage. So the acceptance test stage, this is testing in a production-like environment with life-like scenarios. You're going to configure the environment, deploy a release candidate that was built before, the installer. You're going to smoke test and health check just to make sure it's up and running, ready for use, and then we're going to run the tests. We're looking in on the whole, for the whole cycle, to be somewhere in the order of about an hour. So we want this stage ideally to be in the order of not over 45 minutes. Ideally, that's what we're trying to achieve. Deploying the software, getting it up and running, and then doing all of the tests that you can think of. Scary, but... Right, so a good way of thinking about this is the rates of change of things. So think about separating out the rate at which things change. So your user interface is probably going to be changing more frequently than your database schema, which is probably going to be changing more frequently than the version of the operating system, maybe. I don't know. So think about the rates of change and maybe layer the deployment. So you only have to, so you do incremental deployment, incremental configuration management. Modern container systems will do some of this work for you by layering the stuff internally, so you can kind of allow them to do some of the heavy lifting for that sort of stuff. But if not, that's a good technique to think about, is layering things so you can change things. So you can kind of start thinking about creating an image for your server, and then you just make the small changes of your application on top of that image. Those sorts of things.
What's the scope then?
What's the scope?
Yeah, because the base layer is the operating system. The operating system changes, your top of the cake stops working.
Well, every change goes through the pipeline. So your operating system change goes through the pipeline, and it's going to fail in the test environment first. So the point at which we deploy. So if you need to change the operating system, that's going to be part of your deployment. So you'll deploy that layer, but that's going to take a little bit longer, and you'll take that cost. So you're trying to share out the costs, the time costs, I suppose, for that one build. The one where you change the operating system, that one build is going to be a little bit slower. But how you do more work, so that's not bad. So think about layering the configuration as a technique to be able to separate these things out and allow you to go more quickly. Thinking of versioning these kind of pre-baked templates and kind of cookie cuttering out those. One of the things I've had some success with a recent client is to make a pool of those in advance, because it took a while for them, given the technology that they were using to actually create the images. They pre-baked the images, so they had a little pool of images ready for deployment, and then they could just pull those down, and then in the background there's some other process somewhere that was just repopulating the pool with images for the next deployment. That worked quite nicely. So you can think about these sorts of things, sort of sharing out the work to just, again, keep the feedback. Consider the use of containers like Docker. It will sort of simplify some of these sorts of problems and help you out with some of these sort of techniques. It's not a silver bullet, again, of course. So, successful deployment ends with a running, working system. So, for efficiency, we must think about the time to deploy the system itself. As I said before, we'd like to kind of shift the if we want it to be efficient, we'd like to shift the minimum number of bytes. So think about that, think about how to do that. The time to migrate data, I think there are different ways that you can think about data migration. to accomplish those. The time to start the system up. Our system, when we were building the Exchange, because we wanted the feedback from the test, would start up in about, it would start up and be populated with state in about 2 seconds. And this is like a fully loaded, very statefully rich trading system, which was remarkable, really. But that was an outcome of the testing, and it meant that when if something broke in production, we could bring something down and bring it up and minimise the disruption as well. So we got these knock-on good effects. And the time to validate the systems. You also want to, once it's up and running, you want to check that it's up and running and ready for use, and you want that to be fast and efficient too. So keep the deployable artifacts lean, keep them as small as possible. Packaging strategy can make a big difference. Thinking about how you compartmentalise these things and using techniques like pools of things that change at different rates and all those sorts of things can help you manage this differently, and that can make a difference. Think about network infrastructure and the constraints that gives you. I worked with some teams that were doing some deployments to parts of the world where the bandwidth of the networks was really slow. So we were trying to think about how we built that into our thinking about deploying things, because that had a serious impact on how quickly you could shift bytes around. So you need to think, you need to apply your software engineering brains to these sorts of problems. Minimize data sets wherever you can. I'm a big fan in automated testing of synthetic data. I really seriously dislike, on the whole, just taking dumps of production data and running them through the system. Think about better modularization and better independence. This is kind of counter to the previous advice about splitting things out, but it is a viable strategy. You've got to understand it and take the consequences, but it's worth considering. Okay, so we're going to minimise the startup dependencies and ordering. Those are important things if you want to start things. Ideally, certainly for a distributed system, we'd like to kind of deploy it as a distributed system. Have all the things go out and all start up, and then that's going to be more efficient than things being sequenced and waiting for one thing or another to happen. That has an implication on architectures and coupling, communication strategies, all these sorts of things. But these are things that are worth thinking about as you start taking this fast feedback system. And again, this is one of those sorts of subtle things. It has from my perspective, I think it has a beneficial pressure on the architecture of your system. I think you end up building better systems when you start forced to take these sorts of things into consideration. Invest in optimizing code executed during startup. Make it efficient. Make it fast and as efficient as you can. Again, that's going to pay back through the testing, but you'll get these other knock-on benefits as well. Think about better modularization. Do start thinking about, how can we isolate these things? Can we really decouple those things so we could deploy things more independently? And start considering that. Remember, it's difficult, but it's worth exploring. So there's a common cycle in terms of acceptance tests. We talked earlier about kind of the ever-growing number of tests that you have. And this is doubly true of acceptance tests, because these are big, expensive things. You're going to be starting up a whole system, and you're going to be running these relatively long, complicated scenarios against this lifelike semi-production system. It's going to have fake parts of it, so you can collect inputs and fake inputs and collect outputs, but largely it's going to be production. And what nearly everybody does when they start out using this, they're going to have, we've got a server to run our acceptance tests. So they'll run all the tests on the acceptance test, and then after a bit, it's a bit slow, the feedback's slow. So they buy another server. Nearly always, that's what happens. And the first off, what you'll do is that you'll just manually divide your tests up. Because it's the obvious thing to do. You've only got 2 servers, so you run half your tests on one server and half the tests on the other. One server is probably always going to finish a little bit back the edge, and you might juggle a little bit to try and get them more evenly. But that's where you're going to run for a bit. And then, after a bit longer, it slows down again, you buy another 2 servers. And at this point, you start to get bored, or at least the person whose job it is to distribute the tests and level them all out starts to get bored. And so you probably end up starting to automate this, and you build a test allocator. We wrote a distributed grid computing system just specifically for tests that would allocate tests to a build grid. So you would arbitrarily have a number of servers responsible for running tests, and then at runtime, our code was called a Romero, it would just allocate tests to the system dynamically. I think I've got a little illustration. So one of the things that really gets in the way of this is if your tests are badly isolated. If there are dependencies between them or data leakage between them, that can really get in the way of your ability to do this. So keep the tests isolated from day one, and then at the point at which you need to go more and more parallel, it's an easy job to do. Again, I refer you to my my other talk on acceptance testing to go into that. That goes into that in a minute. So test avoidance is a good idea. Some of the biggest companies in the world, they work by test avoidance. What that is doing some kind of analysis on your change and deciding what tests are going to be affected by that change and only running those tests rather than running the whole test in the universe. That works. I confess, personally, I've never been able to make it work. And that's just because I wasn't clever enough to come up with a good way of it happening. The times when I did it, on the teams that I worked on, when we measured it, we found that we were spending more time figuring out which tests to run than it took us to run the tests. So we just ran all of the tests because that was easier. We just did the brute force thing. That's worth thinking about. And certainly there are some stories, I think Google are probably the seminal example of doing this on massive scale. And if I'm honest, I don't know the mechanisms that they use to do test avoidance, but it works for them. Acceptance tests, though, are really valuable. I don't know a team that's really taken these seriously and adopted this style of development that would drop the acceptance test, because they give you a different kind of insight into your code. I think I'm one of the biggest fans of test-driven development that's out there. I think it's really seriously important in terms of the quality of work. But acceptance tests add to that. They give you this different picture. So you need to be careful not to spend too much time trying to avoid it. If you do all of this, you can kind of do the scale-up thing. You can kind of start to think about the multiple servers. So you have a change, it arrives in the artifact repository, the acceptance test environment becomes free. It picks up the newest change that was in the artifact repository, deploys that to a test environment, spins out a whole bunch of test hosts that runs against it, and collects feedback and reports back, collects the feedback and synthesizes it and reports back against the chain, the release timeline. This is the visualization that I was talking about of our test runner doing that. So we've got a bunch of tests that are running in parallel. So we've got sequential parallel. So we've got here, we've got a bunch of tests that are running in parallel, and they're being shared by different test hosts in here. Here we've got a bunch of other tests where they're doing time travel tests and destructive tests, where we don't want to share the environments and they're dedicated, and so on. And you can see the tests running and the network being reconfigured and dynamically reallocated to kind of balance the load of the test environment. Failing tests. So, the efficiency of the feedback cycle is central to our ability to stay on top of, to keep tests running. And so we need to really think about these times. The longer it takes us to get that feedback, the more failing tests we'll end up living with, is the subjective impression that I get from having seen lots of teams trying to do them. If you can keep it down to those sorts of numbers, you're in a very good place to be able to stay on top of test failures all of the time, and your build will be green nearly all of the time. And that's where you want to be. So continuous delivery is about keeping the build in a releasable state all of the time. So you have to prioritize failing tests. They're the number one impediment. As soon as you commit something that breaks the pipeline, you're now in the way of every other developer using the pipeline. So you've got to get out of their way. So you've got to get the change. So you commit a fix or a reversion. Intermittent tests are the bane. This is usually less. Sometimes you get these sorts of things with especially time-based tests and that kind of stuff in unit tests, but mostly it's not in unit tests. The real pain for intermittent tests are the bigger, more complicated acceptance tests and performance tests, those sorts of things, and they're a real annoyance. I think too many teams just live with the pain, and so what they do is that they'll have a bunch of tests, and you'll make a change, and the tests will fail, and they'll say, "Oh yeah, that one always fails. Doesn't matter. We'll release that fine." Some of the build tools do something that I absolutely hate. So you can configure Jenkins and TeamCity and Bamboo and those sorts of tools to run your test. If your test fails, it'll run it again. Which one's telling you the truth? If it failed once and passed once, which one's honest? I don't know. You're in an indeterminate state. If a test fails, that's it. End of game. Throw it out the pipeline. Go back to the start of the pipeline and start again. Commit a change that makes it work. If the test is flaky, fix the flaky test. That's much easier said than done. So, yeah, so that's the point I just made. So don't live with intermittent tests, solve the problem. There's one of these patterns. 9 times out of 10, the failing test is going to be a trivial, silly thing in the test itself. And you'll usually catch that quite quickly if you look at it and fix the problem. And then, the other 1 time out of 10, it's going to be a really annoying thing that you can't find out, and you'll be trying to add telemetry, and you'll be trying to dig in and trying to find out. We had some tests that it took us literally a couple of months to get to the bottom of, one way or another, trying to look into it in different ways. Every time, once you get beyond a certain threshold of quality, every single one of those occasions, it was something real. It was a real problem in the production system that would have come along and bitten us in the future had we left it there at some point. And so it's worth the effort. It's worth the effort going in and trying to find out what's going on. Quickly eliminate the dross of the poorly written tests and stabilize those using domain-specific language techniques and stuff. Watch the acceptance test. But then start taking the intermittencies fairly seriously. Treat them as failing tests. Always treat them as a failing test. If it's intermittent, it's failing. Even if it's passing and it's intermittent, it's failing. Track the history of your tests. Have a little tool. We implemented a tool which was called Auto Trish because we had a woman called Trish on the team that used to do it manually for a while, and we automated it. And it just used to give us a little time horizon. It used to show you a little graphical picture of the last 10 builds, and you could see the pattern. That one goes pass, fail, pass, fail, pass, fail. That one goes pass, pass, fail, pass, pass, fail. You can kind of see that it wasn't quite that simple, but you could see patterns, and you could see candidates. We used to give it a Trish index. of how risky it was to be an intermittent test, and then we could prioritise it and dig in. Last resort, if you really can't fix it, delete it, because it's lying to you, and it's better to get it off the board than to leave it there. If you're living with failing tests, what that's saying to the culture of the team is it's okay for tests to fail. There's a really distinct difference in the behaviour of a team where the build's always green versus the behaviour of a team where there's a proportion of the tests that are always red. And that's really hard to get over as long as there are failing tests. You want to get those failing tests off the board. Correct, you don't really want to throw them away, but this is a last resort, but it's a real last resort. It's better to throw it away and have a green build than it is to have a build that's lying to you and you're working on the basis of mythology rather than measurement.
So no manual approval on failing tests?
No manual approval on failing tests. No, I don't agree with that. I don't think anybody's smart enough to know. Don't get me wrong, I've done it.
I agree with you.
Yeah, and don't get me wrong, I've done it, but and it's like, yeah, that one's okay, and then you find out later, it wasn't. So common causes of intermittencies, just to kind of give you some pointers to look for. Race conditions, particularly in distributed systems, that's really common. Poor test isolation, data leaking between test cases. Poorly designed test cases themselves, where there are problems in the test case itself. And every now and again, it's something serious. There's a real bug in the system, and you'll be really pleased when you find it, when you dig in. Prioritise fixing intermittent tests. This is one of the things that we failed at for a very long time on the LMAX project. We lived with these. We built our auto trish. We lived with a degree of failing tests for way too long. And eventually we bit the bullet and we started really digging in and fixing them when they cropped up. And it made a big difference, made a significant difference to both keeping the test green, but also to the confidence that we had and the speed with which we could move it, the more subtle things that have an impact. Finally, pipeline changes. So the deployment pipelines is strategic rules. As we talked about earlier, if we want to make a change to it and that change fails, then we're screwed. We can't get any change into production. We can't really safely even make any change in development because we're blind to what's happening with everybody else. We've lost the benefits of continuous integration. So we're in a dangerous situation. So you will probably want to start thinking about redundancy and clustering in highly available systems for your pipeline. You certainly want to think about infrastructure as code, so you can kind of blow them away. You certainly want to think about version controlling the configuration of your deployment pipelines. One of the things that's kind of amused me and appalled me, I think they've got better recently, but until relatively recently, a lot of the build management systems, you couldn't really version control them very well, which is crazy. You have to go through hurdles to version control them well. I think they're getting better now, but that ought to be absolutely fundamental. I confess, I've got hardline enough that if anybody wants to introduce a third-party technology to my production system of any kind, my first question is, how do I version it, and how do I automate its deployment? And if I can't do either of those things, it's off the table before I even look at what it does. Unless I'm absolutely forced into doing it for some reason. That's how important this stuff is. So we want to be able to do these sorts of things and treat them seriously. So the pipeline is a complex system in its own right. And if there's some people in the room that are ahead of me, yes, I have built deployment pipelines for deployment pipelines. And it worked really well. One of the companies I worked in, we were doing continuous delivery as a service. We were building deployment pipelines for various teams. And we built a deployment pipeline with a little fake project that would run through really quickly and just say any change that we made, it would run through it all. Use continuous delivery practices for the deployment pipeline. It works really well. I think it's well worth considering doing that, particularly if you're in a large organisation. Think about versioning it and your tools, and think about using the approach. Think about test cases. Think about test-driven development for these infrastructure changes. That's kind of bleeding edge at some level, but that too really works. We came up with a little unit testing framework for writing shell scripts because we wanted to be able to do TDD on the shell scripts that we were building for our pipeline. Think about blue-green deployments where you kind of can provision and configure one environment, get it ready for use, and then switch it over to be the production environment. So you're using blue, and then next time you update green, and then you switch that over. That's a very good strategy for deployment pipelines. Infrastructure as code for all of the pipeline hosts, I think, is probably table stakes. I think, you must be able to recreate those environments from scratch and version everything, step back to same place. And finally, make sure that the pipeline is your only route to production. Any production that goes around the edges of the pipeline is dangerous. It kind of can screw you up. So one of the things that I think that the cloud brings is the kind of the real hardline immutable infrastructure thing where you just throw away previous environments and re-establish them. So any changes that anybody does sneak in somewhere else, they're going to be blown away next time you deploy. So if you do all of that, I think you get to this, and that's this continuous delivery as a commercial competitive advantage. This allows us to carry out these experiments, in the code with ideas, taking them out to users and evaluating what's going on. I'm really sorry, I'm very seriously overrunning time. It's because of the interesting questions.
Sorry.
Thank you very much.